All right, I'm going to pick up where y'all left off. We're on example 14. Divide x to the fourth minus by 2x squared. Write your results in two different ways. So first of all, we have to use long division here because we're dividing by a quadratic. And synthetic division only works when we divide by a linear function. And we have to divide by a single root. We can only synthetic divide one at a time. So if you ever divide by something that's bigger than degree 1, a linear factor, you have to use long division. The next thing that you want to do, as we've already stated here, is to make sure you write everything in descending order of degree. You can have a placeholder if you want. Like in synthetic division, we need the placeholder for the iterations to work. Here, you don't have to have a placeholder for the missing x cubed. You just have to realize you can only add like terms when you subtract. Okay, but they do need to be in descending order. So the dividend goes inside the house, and the divisor goes outside the house. You look at the first two terms. How many times does 2x squared go into 8x to the fourth? That's the same question as off to the side. What's 8x to the fourth divided by 2x squared? That gives you 4x squared, and that goes on top. Now you distribute, which is where we're at, and that gives you 8x to the fourth. So at this point, those two should be the same. And then we get minus 4x cubed, and then we're going to get plus 8x squared. Okay, now I draw the line and I flip all the signs because I'm subtracting. So that becomes negative, that becomes positive, that becomes negative, and I add like terms vertically. And that's the important thing. I have to add like terms. Add like terms. So the 8x to the fourth should cancel. By design, that should always be the case. And then what would be the next degree? X cubed, right? I don't have an x cubed in the top, but I have a plus 4x cubed, so I'm going to write plus 4x cubed. And then I have a 6x squared minus an 8x squared. That's a negative 2x squared. And then I can just bring down the other two, minus 3x plus 1. You can bring everything else down. Okay? I combine these two guys right here, the plus 6x squared and the minus 8x squared. That gives me the minus 2x squared. So we have to add like terms. All right, now I do it again. So I say, how many times does 2x squared? Not with a highlighter, stupid highlighter. How many times does 2x squared go into 4x cubed? 2x, okay, so that's plus 2x. And you'll know it's right because when you distribute from up top now, you should get a 4x cubed. Those numbers should be the same. And they are, so I did it correctly. So then 2x times negative x is minus 2x squared. And then I get plus 4x. And then I change all the signs. I subtract, so that becomes minus, plus, and minus. The 4x cubes cancel. And lo and behold, the 2x squareds cancel. That wasn't a guarantee, but they did. And I'm just left with negative 7x plus 1. Now, does 2x squared go into x to the first? No. Had there been another x squared term here, I could have done one more iteration. Because x squared will go into x squared a constant amount of times. But x squared, which is degree 2, does not divide into x to the first anymore because now my divisor is larger than the quotient. Okay, so this is all I can do. Now remember what that means is this. Here's how I can state it. I can say 8x to the fourth plus 6x squared. I'll just go to the original one. Plus 1 minus 3x. Plus 1 minus 3x. That's the original dividend. Divided by 2x squared plus 2 minus x. I'm just referring up here to the top to the original functions. That is equal to the quotient 4x squared plus 2x. Yes, yes, the quotient. And then plus the remainder, which is negative 7x plus 1. That's our remainder over the original divisor, 2x squared minus x plus 2. Okay? Yeah, you could do that. Well, in this case, so is kind of when it's a result of some logical consequence. Like I did this, and now this implies this. I just kind of did the work here, and I'm summarizing my work. So if you want to put so, you can. So let's do it. Do you have to? Let's say yes. Let's say yes, you have to. I didn't put that. I put an asterisk, but so works just as well. Or here's the other version of it. If I simply take this entire equation and multiply both sides by the divisor, the denominator, I get the other version of it, which is going to be 8. Oh, stupid highlighter. I hate that. 8x to the fourth plus 6x squared plus 1 minus 3x. It divides out on the left side. When I distribute it, I get the factor 4x squared plus 2x times the divisor 2x squared plus 2 minus x. So it's that times that, and then it divides out in that last term, and I just get plus the remainder, which I can just say is minus 7x plus 1. Yeah, either way is fine. I like the top version better. The bottom was an easier one to verify. Like, if you want in the bottom, you actually can FOIL or expand these two things out. You can multiply them together, combine like terms, and then add 7x plus 1, and you'll see that you get the original. Okay? All right. So those are the two different versions. So synthetic division, as well as it works, doesn't always work, does it? It works when we're dividing by a single linear factor, x to the first. If you're dividing by something that's degree 2 or larger, you got to go back to the good old-fashioned long division. Unless you can factor the quadratic factor here and divide out each factor one at a time, but I don't think that factors. Okay. It was fun? I would say this is fun cube. This one on the fun scale is probably fun cube. The next one is almost too easy to be fun. You know, sometimes something's too easy, it can't be fun. It's like walking through the door this morning. That wasn't very fun. It was fun when we got here, but the actual walking through the door was way too easy. That wasn't that fun. It was not memorable. If x plus 2 is a factor of this cubic polynomial, find the value of k. This is the last one we're doing. Okay, let's think about what the factor theorem says. It says if x plus 2 is a factor, then x equals negative 2 is a root. Yes, yes? Which means, we're just kind of going logical consequence here, which means f of negative 2 must equal what? 0. Okay? So I have two ways that I can evaluate f of negative 2. I can do direct substitution, which we learned yesterday that sometimes direct substitution is actually a lot nicer than synthetic substitution. Yes, yes? Let's retreat and see which example that was. That was on example 12. I did not want to plug in a negative 1 synthetically because that would have meant a lot of placeholder zeros. So I used direct substitution. Okay? Let's see what direct substitution would look like here. All I'm going to do is I'm going to use this fact right here to make that into a numeric equation. So I'm going to set f of x equal to 0, and I'm going to plug a 2 in for x. So I get 3 times negative 2 cubed plus the unknown k times negative 2 squared plus negative 2 minus 2. Does everyone see what I'm doing there? I'm plugging a negative 2 in for x, and I'm setting it equal to 0. Because x plus 2 is a factor, x equals negative 2 is the root. Now, this one requires a little bit of, like I said, we have 4 terms. We've got to treat each of the 4 terms as its own problem to begin with. Negative 2 cubed is negative 8, and negative 8 times 3 is negative 24. So I get negative 24 there. In the next term, negative 2 squared is 4, so I get plus 4k. And then I get minus 2 minus 2. All right, now I can simplify by adding like terms. So I get minus 24, minus 26, minus 28. So 0 equals minus 28 plus 4k. I'll bring the 28 across, and I get 28 equals 4k. And now I'll divide through by the 4, and I get k equals what? 7. There it is. Oh, yeah, we're going to do that next. I'm going to let you decide here which one you prefer. I think on example 12, unless you're crazy with a capital K, I don't think anyone preferred synthetic division there, right? Everyone's going to prefer direct substitution. But for a problem like this, it's almost like 6 of one, a half dozen of the other, right? It's really kind of the same thing. It's just up to your preference. Let's just try the synthetic version.
Is the test going to say, like, do one direct or do one direct substitution and one synthetic substitution?
More than likely, no. You'd be able to choose. I would like for you to be able to choose which method. Yeah, because that's yeah. I'd like for you to know how to do both methods, but I might set up a problem like example 12 where you're encouraged just by the nature of the problem to do one version over the other. Does that make sense? Yeah. But if it's a problem like this, it would probably read exactly as it says here. Now here's what synthetic substitution would look like. I write out the coefficients of f of x in descending order with a placeholder for anything that might be missing. So I got 3, I got k, I got 1, and I got -2. And I synthetically divide with what? -2. So I put that in the box out front, and I have to force my last box to be what? That better equals 0 when it's all said and done. That better equals 0. Okay, so let's go ahead and do the synthetic process here. Bring down the 3, and I multiply and I get -6. Now what's k minus 6? I don't know. I just write it as k minus 6. Okay, and now I multiply, which means I distribute, and I get -2k plus 12. Everyone okay with that? See what I did? I just multiplied the -2 times the quantity, k minus 6, and now I add like terms, and I get -2k plus 13. And then I distribute the -2 again, and I get 4k minus 26. And if I add vertically with like terms, I get 4k minus 28. And because that's the remainder for any value of k, and I want it to be a factor, I need to force the remainder to be 0. Well, guess what linear equation I have now set up? I get 4k minus 28 has to equal 0, 4k has to equal 28, and k must equal what? 7. So which method do you prefer? Boy, I can make an argument for either one of them. They are both equally delicious to my mathematical palate. You work backwards? Yeah, that's fine too. Yeah, you can work backwards from synthetic division if you'd like to do that as well. Instead of going forward with your polynomial version of k, you can work backwards from synthetic division. You know it has to equal 0, so you know that has to equal -2. That's fine too. I'm fine with you doing that as well. That means you're understanding the process. Okay, that concludes the notes. How do y'all feel about real zeros of polynomial functions? Pretty good. Okay, well, you have the rest of the period to work on your worksheet. So the worksheet for section 3.2 is going to be due on Monday at 9 a.m. Okay. Now we're going to skip section 3.3 for now. So on Monday, we're going to start section 3.4. I've already activated that in Canvas. If you got an alert that 3.4 is active, that's why. It will take a few days on 3.4. On Thursday, we're going to review sections 3.1 through sections 3.4. And then on Friday, which I think is November 3rd, holy moly. I believe that's, is that next Friday? Yeah, it is almost Christmas. Friday, November 3rd, we're going to test on sections 3.1 to section 3.4. Next week is already the 3rd week of the 9 weeks grading period, so we need to squeeze in a test. So we'll squeeze one in on Friday. Now, section 3.4 is going to build upon everything that we've done in section 3.2. We're just going to do it for not just real roots, but we're going to do it for imaginary roots as well. And so if you think you like synthetic division now, boy howdy, you just wait. You're going to learn to love it in 3.4. You're either going to love it or you're going to love to hate it. But there's going to be love involved, I guarantee. All right. Comments or questions? Okay. Well, we're done. You have the rest of the period to work on your assignment. I'm here if you have any questions.